Now we said before, and let me go back up here and say that the reaction favors the reactants right here, simply because the aldehyde is more stable than the hydrate. So again, the product of this is the hydrate, but if you notice the arrow here, the equilibrium, and let me write that down, equilibrium favors the aldehyde or ketone if you have a ketone. However, that doesn't mean that we can increase the likelihood of forming the hydrate. We can do that, but we have to look at a few factors as we discuss here. So the factors that favor the addition, the formation of the hydrate, is that the more stable the carbonyl compound, the less favorable the addition. So again, if the aldehyde and the ketone are more stable to begin with, if they're even more stable or there are more stabilization effects, then the reaction won't take place. The more sterically hindered the carbonyl compound, the less favorable the addition. So again, there are factors that again can make the addition favorable and thus forming the hydrate. So let's look at some of these. You will see in here that some will favor the hydrate more so than the others. So let's look. So let's start with the first one. A little more space here. So we have a comparison between an aldehyde and a ketone. We have acetone and we have acetaldehyde. So if we recall from before that the carbonyl has a delta plus, carbonyl carbon, and then the oxygen has a delta minus, and once again a delta plus. That's on the carbon. So let's recall what we learned about electron donating groups and electron withdrawing groups. If you look here, we have a methyl, which is an electron donating group. So we say we have 1 E D G. And if you recall, the electron donating group, they donate electron density toward that carbonyl carbon, which makes it less positive. So again, 1 EDG makes carbon less positive. Also, in terms of sterics, hydrogen is a small atom. We do have a methyl, but it's not as sterically hindered as having 2 methyls like in the next example. So it's less sterically hindered. Now, on the other hand, let's take a look at this one. Here we have 2 EDGs, electron donating groups. So what do you think? This makes, they both donate toward that carbonyl carbon, which even make it more stable. They make it less positive, even more less positive, and more stable. So you have two EDGs make carbon even less positive. Means it's more stable. Also, these two large groups, the methyl groups, they block the attack more so than having just one methyl group. The hydrogen is small, so this is more sterically hindered. And what do you think? If it's more stable, more sterically hindered, do you think the attack is more favored or less favored? The attack will be less favored. So we will say that this is less subject to nucleophilic attack because it's less electrophilic. So it's more stable, we said. And if the ketone is more stable, then that only means the hydrate is less favored. So you are more likely to form a hydrate from this one than this one, simply because all of the factors here make the ketone, the acetone, more stable. Thus, the reaction won't likely to take place, or even if it does, it's going to be the equilibrium will still favor the reactant. So that's the idea here. Now let's go to the next one. And in the next one, as you can see, you have also a comparison, but we have two aldehydes that we're comparing, not an aldehyde and a ketone. So this one is similar to what we talked about above, same as above. Right here. But what's happening here? Once again, we have a delta positive. Oxygen is a delta negative. Very well. So what's happening here? Well, we have an electron withdrawing group. This is an electron withdrawing group. CF3 is an EWG. Simply because you have these electronegative fluorine atoms withdrawing electrons away from the carbonyl carbon, and of course toward the fluorines. So that's an inductive effect, just like with the electron donating group. So what do you think? If this is already positive and you're taking away electron density from it, it's going to become more positive. So that's not good for its stability. So the EWG fluorine make, and we have to distinguish here, make carbonyl carbon more positive. And we know if we have more positive, that means it's more electrophilic, less stable. And of course, if it's more stable, more electrophilic, I meant, meaning the nucleophile will attack more readily. So this will be more subject to nucleophilic attack. So therefore, the hydrate is more favored. So once again, we're going from the concept that we are looking for factors that make the aldehyde or the ketone, whatever you're beginning with, less stable so that the hydrate would be more favored. Because remember, you're trying to achieve more stability. So again, if it is less stable, the carbonyl carbon, it's more electrophilic, and then the attack will take place in equilibrium. Now, of course, the last one, same as above with this one, but you probably can decide, you should be able to maybe pause and decide which one, whether this would favor the formation of the hydrate or it would be less, or the hydrate would be less favored. So again, look at, are there stabilization effects? Are there effects that make it more stable? So let's take a look at this. And we have a benzene ring attached to this. So so we have a delta positive and we have a delta negative. So ask yourself, what could this benzene ring do? Would it withdraw electrons away from the carbonyl carbon, or would it donate it somehow? So it's going to donate it by what? By resonance. So let's draw just one resonance structure here. You can draw the other ones. So we've done this in chapter 18, if you remember. So notice what happened here. You have resonance stabilization. You can draw more resonance structures. You should be able to draw them. So again, it's making the carbonyl actually more stable. So in this case, this is, we say, resonance stabilized carbonyl. carbon. If it's resonance stabilized, it's more stable. And that equals to less electrophilic. So if it's less electrophilic, then the hydrate is less favored. So if you were to summarize this in a few words, is you would say the more stable the aldehyde, the ketone are, the less favored the formation of the hydrate is or will be. So look for stabilization effects or destabilization effects. If you have stabilization effects, then the hydrate won't form or it will be less favored. If you have destabilization effects, such as the electron withdrawing group, then of course the hydrate is more favored.